Oh, so I started recording. Good morning to everyone. I hope you had a wonderful week. I had a wonderful week. I mean, with this weather, we cannot complain, right? So it was pretty nice. And this time, so while normally we do a sort of review on Monday of the classes, this time we didn't have a time because it was a holiday. And so today we are going to do a quick review of the classes that you should have done during the week. Just a reminder that tonight at midnight, 11:55 is the time where you have to submit your homework. So please remember to do it. Don't forget. And last time there was a question from one of you about the homework. And I don't know if Mike, you want to start with that one.
Actually, I'm sorry, I don't have it prepped and ready to pull up. Can we come back to it a little bit later? All right,
Yeah,
I'll pull it up on another screen.
Yeah, so let's start with the first with the classes, with the lectures that you were supposed to follow this week. And then we will go to that particular question of the homework when Mike is ready. Okay, so this week we have a graphing positions and velocity, lecture number 4. So again, as you see, I'm going to repeat it simply because some of the students joined the course later. So this is lecture 4 and is connected with the tutorial number 4 and with the online homework 4. What you are supposed to do after you look at the lecture, the slides, which you can find in Laulima, and the videos that you can find in YouTube, you are supposed to do right away the homework. So here, what is velocity and position relationship? So what you are supposed to do always is like a sort of graph you see here. So you put
actually, Veronica, I don't think we're screen sharing right now.
Oh, sorry.
Okay,
so I was just giving pleasure to myself.
If I could just quickly say, our LA's Julia and Carlos are with us today, and I think they're going to be here for future lectures as well, Monday, Friday lectures. So if people type things into the chat box, Julia or Carlos will probably be the ones to reply to most of it. Thank you.
Very good. Thank you. Now, can you see my screen?
Yes, thank you.
I'm still doing things on my own. Okay. So what we were saying, lecture 4, as you see here, is graphing position and velocity. This is the reference to the textbook section, the one in orange. So you can have a look at there and read what it's about. And then the related material is also tutorial number 4 and online homework number 4. So you normally, what you have to do, you look at the slides, you watch the video on YouTube, you do the tutorial to see if you are to become proficient with the material, and then you do the online homework right away without waiting, because like this, that part is done. And then you go to the following lecture. So for this lecture, we have velocity position relationship. What I was saying to you, it's very, very important that you always try to make a graph of the situation. So here, as you see in the bottom right, we have the x-axis here, start from 0, which means the 0 position, and then the origin, and then you have the time in this direction. Okay, normally it's taken always a positive axis going to the right and going up, but you are in the future, you can use whatever information you prefer, whatever reference axis you prefer, as long as you are consistent and coherent with yourself. So the average velocity is the displacement per time elapsed. So average velocity is delta x over delta t. Remember, we saw last time delta x is specifically final position minus initial position. You cannot swap these two, or you are going to have a different value. So it needs to be the final position minus the initial position. So here, even looking at this graph, we are going to say that the final position must be this a bit below 300, right? And why do we say that? Because we see that this is associated with the time that is increasing. So the final position must be this one. the initial position must be x1. So you do x2 minus x1. And this is delta x. Delta t, again, because it's a delta, when there is a delta, always t final minus t initial, x final minus x initial. So again, delta t is t final, that in this case is t2, minus the initial one, t1 in this case, or for example, here it could be also 0, because actually here is starting from 0. So let me rephrase this. The final one, I mean, if we want to see which one is T2 versus NX2, we could consider the 0 and just have X2 minus 0 or T2 minus 0. So it depends if you start from 0 or if you start from here. So essentially, you have that the average velocity looks like an equation for the slope of a line. So what you get, because here you have a ratio of these two, the average velocity is just the slope. So you see that this slope here is bigger than this slope here. This means that the average velocity here is going to be bigger than this one, right? So while the instantaneous velocity is the derivative, it means is the tangent in that particular moment. So you know also when you drive the car, you have something which is the instant velocity, which is what you actually see in your meter, your velocity at that moment, at that specific moment, which is different from the average, that is from the final position minus the initial position. Okay, so and the tangent of the slope, so while the slope is the average velocity, the tangent to that particular time, so here we have this one is the instantaneous velocity in the point A, in the point B1 will be again the tangent to this point. This one is called instantaneous velocity, and you achieve it, you find it doing the derivative. So if we look at this graph, for example, velocity position relationship again, what can you say about point A, B, C, D, and E? So for example, let's start with C. C, if we start with C, what do you see? That I have the time is passing by, right? And the position in this position here is still the same. So here, the slope is essentially 0, and which means that the velocity is 0. So if the velocity is 0, it means that I'm stuck in that position, right? So C is pretty easy to understand. But at the same, if we go back to A, so what we see is that in this position, we are starting from a position which is negative position, initial position, which could be at this point the grocery store. So when I'm at the grocery store here, I have a certain velocity because you see the instantaneous velocity in the tangent. And if you go to A, from A to B, you can also measure the average velocity, which is going to be the slope right here. So here you see that all this velocity is positive. And because x is increasing in this direction, so the velocity is in the same direction of the displacement. And you see that here is positive. Here I stop, in the point C I stop, and then the velocity becomes negative because the slope is negative. So if we want to see here what's happening, you see that we are going at a certain time in this direction toward x. The B point, my instantaneous velocity is bigger than in A, which means that I'm going at a greater velocity. Then I arrive 0, I stop. And after that, the velocity is going in the opposite direction with respect to the displacement here, the original displacement. Okay, possible answers are also this one here. So you could have done VT versus T. And so here is, again, all the slopes. You see all the slopes from A to B. C is in 0 because we said the velocity is in 0. From C to D is like this, is negative, and then D to E is in this way. And another possible answer is this one. So you can just make a nice curve. So at all time, the velocity is equal to the slope in the x versus t graph. And over any interval delta t, the displacement delta t is the net area of the v versus time graph. So essentially, if you want to calculate the slope, here you have, for the calculus, you have the derivative, while if you want to calculate delta x for the calculus, you have the integral between t1 or t2 of the velocity. Here, there are the area of the graphs is the area between functions and horizontal axis. So can be positive or negative. So the net area needs to be the cumulative sum of the area over the interval delta t. So there is no formula for this, but you need to, because you need to keep the sign. So to find the position xt instead of the displacement, we must given the value x naught. So for example, here, x at a certain position t is equal to delta x, so t final minus t naught, and the position in t final minus t naught of delta x plus x naught. So sometimes if you start from the origin, this x naught is going to be 0. But if you don't start from the origin, you start from x naught equal to 10, you have to, of course, consider that. So for all this, don't get scared. There is the tutorial number 4 with all the problems, and you can watch also the solutions. So here we also have some tutorials. We will not go through them because I don't know if we have enough time. But you see some of the things that we just discussed. You can have here some tutorial with the posted solution. So you can follow again, just to give you an idea. This is the position versus t, and you see at the initial position, you see x naught, in this case it's 0 because we are starting from 0. Then we got to a certain position, right? And then we are stuck in this position for a while. And so here, if you have to do the velocity, you'll see that here the velocity is positive. In this part here, because we are stuck, the time is passing by and I'm still in position number 3, which means that my position is not changing. So the velocity must be 0. And then we go to a negative velocity here. And again, in this last part, the velocity stays again at 0. Yeah. Okay. Then another concept is acceleration. So we haven't seen the acceleration yet. So you will have, this is a review quiz that you should do at the beginning. And it gives you an idea if you understood the concept. And this is the review quiz. Okay, so what is the acceleration? We discussed about the position, which means where something is located. We also discussed about the velocity and speed, which represent how fast something is moving, changing its position. And then we speak about now the acceleration. So how fast something is changing its velocity. So here, for example, you have this car that you see in position x1 and then in position x2, and you see that you have a certain velocity v1x at the beginning that then becomes v2x. So if these two velocities are the same, means that there is not acceleration playing a role. So this velocity is just constant and it stays what it is. It might be 0. If it's 0, nothing is changed. It might be constant, and so there is no acceleration involved. But if you see that the velocity changes at some point, it's because there is an acceleration, right? When you are in your car, if you push the accelerator, you are going to see that the velocity change. Or if you decelerate, the velocity is going to decrease. So when you push the two pedals, it's for accelerate or for decrease your velocity, you are actually applying an acceleration. Okay. So how fast something is changing its velocity. So for example, here we see that at t equal 1 second, the car is going 50 kilometers per hour. And then at time 2 seconds is going to 30 kilometers per hour. So you see that there is a change. So because there is a change, there must have been an acceleration here. And then after a few seconds, it goes to a different acceleration. Okay, so the acceleration, as we said before, it can be in the same direction of the velocity, which means that you are really accelerate, or you could be in the opposite direction of your velocity, which means that you are essentially decelerating. So here, I don't know if you want to see this example. If the acceleration maintain a constant value, what will be this car velocity after 1 second, 2 seconds, and 5 seconds? So acceleration here is -2 meter per square per second square. So means that the velocity is decreasing of -2 meter per second every second. So you can just calculate it in this way, saying that at time 1 second, I have V naught, which is the original velocity, minus 2 meters per second, because I'm applying this deceleration. After 2 seconds, I have to apply 2 meters per second minus 2 meters per second again. After 3 seconds, it comes out the same. Now you see how this is a bit inefficient to do, because what if they ask you what will be the velocity after 1 hour? And so there are formulas that combine, make in a compact way what we just did. So in everyday speech, we often use deceleration, which means an acceleration that decreases the speed of an object. So, but deceleration is not always the same thing as negative acceleration. And this is because also depends on the axis, right? So here, I want to give you this final definition. So for the position, we have the location. So this is Cartesian coordinate values. You have to put an X, which is the horizontal axis, or Y, vertical axis, or sometimes you have also 3D, so you need to put also 0. The position is the distance from the origin 0, and you need to use plus and minus sign for the direction. And I think by now you got this. Then we have the velocity, which is the rate of change of the position. We saw that if I'm stuck in a position for a certain period of time, it means that I don't have any velocity. And so while if I change my position, then a velocity must be there. And so how do I find out the value of the velocity? The value of the velocity is provided by delta x over delta t. So with delta x is x final, my final position, minus initial position, divided by the final time where I got to the final position, minus the initial time. The instantaneous velocity, vdt, we already said that is the derivative over time, because it's instantaneous at that particular time. And is the acceleration instead is the rate of change of velocity. So as you can imagine, because it's very similar to the velocity from this point of view, is because it's how change the velocity. So it's going to be delta V over delta T. So delta V means V final velocity minus initial velocity divided by the time where I'm measuring the final velocity minus the time where I measured the initial velocity. So they are very similar. And this you need to learn. Unfortunately, we are going to use them a lot. So my suggestion to you is that you just memorize this equation. The instantaneous acceleration is the derivative of the velocity versus time. Okay. So here, because we did some units, remember we discussed about dimensional equation. So the quantities, the dimensions of the velocity are given by here, delta x, we are speaking about the displacement. So it's going to be meter, right? And divided by something that is seconds. So meter per second, or as you used to hear in the US, when you drive a car, miles per hour, which totally makes sense, right? You have a displacement over a time. The accelerations, which are going to be the units of the acceleration. So because here we have delta V, so we know that our velocity is already meter per second. And now I divide again by another second. So it's going to be meter per second squared, right? Which is the units of an acceleration. Yes. So this, you always write meter per second squared. Okay, sounds good. And again, the velocity can be positive or negative, and the same can be for the acceleration, positive or negative. So here, for example, you have a certain initial velocity. You see that the second velocity is greater. So we are speeding up. And in this position, how is it going to be the acceleration? Now you should be able to say that it's going to be positive. While here, we are slowing down. Indeed, you see that the velocity, initial velocity, is greater than the final velocity. And so you see how it should be the acceleration, negative. So the acceleration in this case, you are really, is in the same direction of the velocity, right? Same direction as the velocity, because you are increasing the velocity. So is in the same direction, while when you are decreasing is in the opposite direction of the velocity. So what's happened here? Here, velocity is negative, right? So here we are leaving from an initial position where we have a negative velocity, which is smaller, with a negative velocity, which is greater. While here, we have the opposite, a negative velocity that is greater, and here we have smaller. So here we have an acceleration, and here we have a deceleration. An acceleration in this case, of course, the acceleration will be in the same direction of the velocity, right? So here you're going to have, because the velocity increased, so the acceleration in this case is going to be negative, same sign of the velocity. In this other case, instead, we see that the velocity is negative because we are going in towards left, so towards the negative side of the displacement of the x-axis. And we see that the velocity is decreasing. So must be something that is decelerating our car, and which is a acceleration that in this case is positive because it needs to go opposite to the direction of the velocity. I hope it's making sense to you. I really hope. So deceleration, this is just to say that deceleration is not always the same thing as negative acceleration, right? We see this. This is negative acceleration in this case, but we are actually accelerating. So it really depends, negative or positive depends on the axis that you choose, the direction of the axis that you choose. So we have other example here. In this case, I would like you to answer. If you would have been in class, you would have to answer. And here instead, I feel like, yeah, I'm doing everything. So what is the car's average acceleration? Is the time, if the time slow shown is 4 seconds, sorry. So here we see V2 and V1. So V1 is the initial one and is minus 15 meters per second. And then we have V2, the final velocity, which is minus 5. So is going in the opposite direction, in the negative direction, and that's why it's negative. You see here, this is final because it's 2, and this is 1. It must be initial because it's 1. So again, we calculate the average acceleration, delta V over delta T, which means V2 minus V1, right? Divided by delta T. Delta T, it says already here that is 4 seconds. It doesn't say if we start from time number 1 second to time number 5 seconds. It just says the value of delta T, which is 4 seconds. And so what you do is V2 is what? Is minus 5 meters per second, right? Minus V1. V1 is minus 15 meters per second, all divided by delta T, which is 4 seconds. Okay, so you have 10 seconds because this one becomes positive, right? Minus times minus, make it plus. So it's like you have minus 5 plus 15, which is plus 10, divided by 4 seconds. It gives you an acceleration 2.5 meters per second square, which is positive. Okay. And why is positive? We already kind of knew that because the car here, you see that is going for a bigger velocity to a smaller velocity. So the acceleration must be in the opposite direction of the velocity. And because the velocity is negative, must have been positive. So it makes sense that it's positive. The value makes sense. And then let's look at the units. So meter per second divided second, meter per second square. And we said that the acceleration is measured in meter per second square, right? So also the dimensions work. So the car is moving backward with respect to the x direction the entire time, but the acceleration is positive. Okay. So let's look again at the average acceleration, which is what we just calculated in this example before, is delta V over delta T. Indeed, we just did it. V final minus V initial. And is the slope of the interval delta T. So if we want to see it, to be able to visualize it, this is V now, is no more X. So pay attention to this because they all look very, very similar. So T, we still have our T, the time here, but here we don't have anymore the displacement X. Now we have the velocity. We put our place B and A, B with a certain V2, A with a certain V1. This we knew from the example of before, T2 minus T1 is 4 seconds. We knew also the value of B and A. So here you can even put your values. And what you have is that the average acceleration is really the slope of this curve. Okay, while the instantaneous velocity acceleration is the slope of the tangent in this particular position, which is given by the second derivative. So already for the velocity, you have to do the derivative versus time of the displacement. For the acceleration, you have to do the derivative versus time of the velocity, which means the double derivative of the positions versus time. So again, from previous lecture, we see that velocity, VDT, is the slope in the x versus t graph. And the displacement delta x is the net area of the v versus t graph, okay? And here we are saying that acceleration is the slope of the v versus t graph. So it is the same concept. And while the change in velocity, delta V, is equal to the net area of the V versus T graph. Here there are some examples that you can do of the they are also the solution in the tutorial. So again, you see, you need to pay a lot of attention now to the axis, because here you have the velocity, and here you always have the time, and here you have the acceleration instead of the position. So for example, let's start with the B. B, we see that the velocity is 50 meters per second, and doesn't change, it's constant, right? So if it's constant, what does it mean? What is going to be our acceleration here? Is going to, in the part B, is going to be 0, right? Because the car is not nor increasing the velocity nor decreasing the velocity. So it's going to be fine. Velocity here is positive. Okay, so we don't know about the acceleration, but it's positive. But to go from this velocity to this, to 0, and then we have here that is negative. So let's see, I don't know if we want to do it this one. Wait a second. So what is the car acceleration during each of the time segment? So we see here there are all the numerical value for the Mike, is this the solution or the
answer is one of those. That's
yes.
just multiple choice answers.
Okay, yeah, this is multiple. So you have to find the for each sentence. So indeed, sorry, I didn't get it at first, but it was an acceleration. So it was supposed to be a solution for sure, because it's asking for the acceleration. So here you need to find which one of these numerical value you have it. So again, you need to calculate, right? Velocity, final velocity minus initial, right? So here the final velocity is 50 divided by the initial velocity, which was 0. And here the time, how much time passed? 20 seconds. So you have to do 50 divided by 20, and you find the acceleration. So I'm just telling you roughly what you need to do, okay? While here, because it's 0, so at the numerator, you have final velocity minus initial velocity. We already said velocity doesn't change, so it's 0 divided by certain times. No matter what, it gives you 0. So here we know for sure that segment B is this one. And then in this one, instead you have the final velocity, which is 20, minus the initial velocity, which was 50. So 20 minus 50 is going to give you something negative, right? So, and indeed, you see that in segment C, you have different values, but they are all negative values of the acceleration. Okay, so, and then you do the, so 20 minus, and next time I will try to do it online with you. Now I just got my iPad to be able to write directly on the slides, but from the next time I will start. So 20 minus the 50, and then divided by the delta t, which is 60 minus 50 is 10 seconds. Oh, here he is, Mike. Yeah, it's so smart, Mike. So cool. Thank you for helping me out. That is awesome. Yeah, I want to do something like that. Perfecto. Perfect. You're awesome. So yeah, you see, so we knew already that it was a negative because the final velocity was smaller with respect to the initial velocity. And so means that the acceleration is in the opposite direction. And because all these velocity are positive, because they are above the 0 here, so they are all positive velocities. So we already knew that that acceleration would have been negative. Okay, sounds terrific. So here they are already, maybe are the solution. And okay, you can practice with some of these. And always keep in mind, yes, that there are these 3 graphs. So X, V, and acceleration. And it really, really matters the direction. So where is the 0 and where is the positive axis? Because sometimes you might also decide to have the axis going in a different direction. It's up to you sometimes to decide how you want to do it. Okay, lecture number 6. So this one was the kinematics of constant acceleration. So there are some review quiz again that you need to do at the beginning to see if you got it. Then we just finished with the definition of the average acceleration. What happened to this equation when the acceleration maintains a constant value over time? We can drop the average and just say A, because A never changes its value, right?
Veronica, actually, this is actually getting ahead. So I think that this is for Monday.
Oh.
Yeah, lecture 6.
Oh,
because we had a holiday. So
yes, okay.
today is through
yes.
lecture 5. Yeah.
Awesome.
I mean,
Yeah.
if you want to stop now, you can stop.
Okay, if you are ready with the homework, it's actually the perfect timing, because if you are ready, before
Yes, I am.
going to the homework, what if we just summarize what were the main questions asked in the chat? Who wants to do that? Carlos, do you want to, for example, say what was asked and what you replied? Because like this, everybody knows.
Actually, Julie and I had been answering the questions at the time they asked them, but students were concerned about the calculus content of the course, which is probably non-existent. And what else?
That's correct.
They were
concepts.
Yes.
I'll just add concepts like slope and the tangent to a curve are general algebra concepts. Okay.
Right.
But we'll never ask anyone to actually take a derivative. The only reason that those are occasionally mentioned on slides, derivatives and integrals, is just because many of the students in the class have already had calculus and they've actually learned this physics in their calc classes. So I just mention it to tie it to those students. But calculus is not a prereq for the class and it's not required to solve any of the problems. Okay, yeah. Thanks, Carlos.
And you know, you will see also in the homework, the level is the same one as the homework. So the calculus that you use is the one of the homework and the recitations. We are not going to come out with the midterms that are, you know, out of the blue. So don't worry. What you see in the homework is pretty much similar to what you will see to the midterms and final. Thank you, Carlos.
Sorry, some students were asking about instantaneous velocity versus average velocity. So I just want to point out that on this slide that's up right now, you can see at the bottom, instantaneous velocity during constant acceleration. So that equation would work for the questions that people were asking in the chat.
Okay, yes. Yes, so they are just going ahead, our students. Oh, we have smart students. Yes, so thank you. Thank you for answering this. Indeed, this is going to be most of the time where we have to use the acceleration. This is going to be the equation that you have to use. And what else? Were there other questions that
there were a lot of questions about like lectures, schedule, and exams and everything. So all of the answers to all of those questions can be found on the calendar and the syllabus under resources on La Lima.
Yes. Yes, and indeed I have here, 1 second, I have the calendar. So indeed, last week we did lecture 2, 1, 2, and 3. And this week, because Monday was holiday, we were supposed to cover only lecture 4 and lecture 5. So I was already going to lecture 6 because I forgot that Monday was a holiday, but lecture 6 is actually for next Monday. So don't worry, only the 2 classes that I covered. And then here, the first week, there was no recitation. There's going to be a recitation this week instead. I believe you already had all your recitation, right? Because it was
Yes,
Tuesday, Wednesday, and
that's right.
Thursday. Very good. And then here in our calendar, we have the homework about lecture 1 to 3, not the material that I covered today. Homework about lecture 1 to 3 that is due tonight at 11:55 p.m. If you don't submit by this time, you will get 0 credit for it, just to remember that. And then while whatever you submit, you're going to get partial credit. So even if you just did a few of this homework, don't worry, it's better than nothing. We are going to have this lecture review of 4 and 5. And then starting from next week, we are going to have a lecture 6, 7, and 8. Okay. Now I'm going to post the lecture today, the recording of these videos, and the lecture for the next time, for the next week online. So you are welcome to watch them before coming to class or after class. This is up to you. And the midterms, because somebody asked about the midterms, the first one is going to be in February 7, and it's going to be on Monday. So essentially at the same time of this lecture on Monday, and it's going to cover lectures 1 to 9. Okay. This was just a recap. Mike, whenever you want to go.
Hi. Okay, great. So what I'm going to do is screen share homework assignment number 3. So this is in Mastering Physics. This one is due tonight at 11:55. Last week, a student asked about one of these runner problems down here at the end. So I just wanted to point out one quick thing. Mastering Physics does not do a very good job of showing when things are extra credit. So I try to add an extra comment here. So this last question here is extra credit. Okay. So it's worth less points and is more work. So it's just want to point that out. And if you don't do it at all, you can still get 100% on this assignment. So that would be beyond 100%. All right, here's the runner problem right here. This is the second to last question on this assignment. It's problem 2.17 is the numbering within Young and Adams. So if we launch it, if we open it here, your exact numerical values will differ because there is numerical randomization in Mastering Physics. So you may have a value other than 290 meters. And your speeds here might be different. I'm not sure. Okay, so they don't randomize necessarily everything. All right, so the question is, suppose that we have a long straight track that's 290 meters long, and 2 runners start from opposite ends, and they run toward each other, runners A and B, and they run toward each other at different speeds. And the question that's asked here is, where will the runners meet? Sorry, why is this working? Okay, here it is. Where will the runners meet? So where along that 290 meter long track will the runners meet, and when will they meet each other? All right, so what I'm going to do is try and create here a quick visualization of what's going on. So this is like step 1 of doing any of these problems. I'm going to define that straight track as the x-axis. And then I'm going to suppose that runner A starts here at the origin, and runner B starts there at 290 meters. Runner A is going to be traveling with a speed. So I'm going to write these as speeds instead of velocities. Speed of 8 meters per second. Now, I'm sorry, I'm going to drop sig figs right now. So all those 0.00s, they're still there. This answer to this problem is going to be a 3 sig fig answer, but it's just going to save me writing on the page, take up less space. And then the speed of runner B is going to be 6 meters per second in the opposite direction. Okay. And the question is, where will they meet? So I'm going to call that X sub M. Right. So that's the part B. That's what part B is asking. And then the answer, and then part A is asking also, what is the time that they will meet? Right. Okay. Well, we know from our kinematics that we've learned so far that if you have a constant or average speed, then our formula for average speed was distance traveled over time elapsed. Okay. Now, in this case, what I want to do is say, all right, in the problem, we're told that the two of them start at the same moment and then they meet at a later same moment. Okay. So that means that the time that is elapsed for each of the two runners is the same. So I want to get this as an expression. Oops. I don't know what just happened here. Okay. All right. I want to get this as an expression for the time. All right. So, and that way I'll be able to equate the time for each of the two runners. For runner A is going to be equal to the distance that runner A travels divided by the speed that runner A is traveling. Okay. And the time for runner B is going to have a similar expression. And then finally, we can use what we're told in the problem, which is that they start at the same moment and then they meet at a later same moment. So we know that the time that elapses for runner A is equal to the time that elapses for runner B. So now I can take each of these expressions and plug them in for the two sides of that equation, right? So let's do that. Distance runner A travels over speed of runner A is distance runner B travels over speed of runner B. So some of these things we know already outright, right? So we know the speed of runner A, that's 8 meters per second. We know the speed of runner B. But what we don't know is the proportion of these two distances, right? But we can define those in terms of x meet. So look, the distance that runner A travels is from the origin 0 to x meet. So that's just going to be x meet. The distance that runner B travels is from 290 to x meet. So that's going to be 290 minus x meet. So let's plug all that in. Okay, now again, I'm going to just drop units and sig figs until the algebra is done. Great. Now I have only one unknown left, and that's x meet, right? So I'm going to do more algebra. And what I end up getting is that the location where they meet is at 165.7 ... meters. Okay. So if I want, I can enter that in mastering physics. I can round to 3 sig figs and enter 166 meters from the starting point of runner A. Now notice I've solved these out of order. Normally, when these questions are asked to you, they're put in an order that is the easiest for you to solve them. But this is an example where the order in which you solve them is actually easier the other way around. So don't be afraid of that. Once in a while, it's easier to find the answer to part B before the answer to part A. Now I can go back and find the answer to part A using either of my two initial formulas over here for the time. Okay, so let's go back to the first formula right here. So I can say that the time that has elapsed, which is the same for both runners, so I can just pick one runner, is equal to the distance that runner A travels over the speed that runner A has traveled. That's 165.7 meters. And the speed of runner A is that turns out to be 20.71 ... seconds. So I could round that off to 3 sig figs, 20.7 seconds. All right, so once again, if you open the same problem in mastering physics, then you will probably have a randomized value. So I think this is randomized. So your 290 will be a different value. So these answers will be close to your answers. These won't exactly be your answers. All right, so this is using sort of two simultaneous equations at the same time. That's why this one is a little tricky. If you have questions about the rest of these, what I'm going to do is encourage you to please drop into, I realize we're out of time, so I encourage you to please drop into our help hours. So our LAs are now, like Julia is going to stay online at this same Zoom address that you're at right now, and she's going to be doing drop-in help hours for the coming hour. Carlos will be on at this same Zoom address later tonight, and all of our other LAs, and including me over here, have hours throughout the week, including some evenings and weekend times. Okay, so please come to us with your questions. Thank you.
And it sounds terrific. Thank you so much. So you see that Mike was kind enough to solve one of your homework problems. So at least this, yeah, but review it what he did, and now you have it in the videos. So I'm going to post the videos after class. Normally YouTube, it takes a while to process them, but you are going to have it in your video. So if you didn't take notes, you can do it later. And yeah, I think that this finishes this class. And thank you so much for being with us. Have a wonderful weekend. Bye.
We're going to stick around because
Much
Julia
for the
will.
LA and Julia and Carlos, and to Mike, of course.
So, yeah, and Julia will stay online. Julia, if you want to take a little 5-minute break, one of us can just keep the channel open, or we can sign off and you can just log in as host again, right? Yeah, that would work too. Whatever works.
I'll sign off and stop the recording, okay?
Okay, that sounds good.
All right, thank you.